Okay, so we're going to determine whether or not the series 1 over n squared plus 1 converges or diverges, and we're going to do this using the integral test. So to use the integral test, we need to check three things. It needs to be positive, it needs to be decreasing, and it needs to be continuous. Okay, so first off, why is this positive? 1 is positive, n squared plus 1 is also positive, so yes, this is in fact going to be positive. Make a check. Okay, second, we need to check that it's decreasing. How can we check that it's decreasing? Well, we can use the derivative. Okay, so if we take the derivative with respect to x of 1 over x squared plus 1. Okay, so we're replacing the n up here with an x down here. Using the chain rule, we should get negative 2x over x squared plus 1 squared. Okay, so negative is always negative, x is positive because n is positive, so this is negative, the numerator is going to be negative, the denominator is a square, so that is always going to be positive. We have a negative over a positive, so that's negative. And if the derivative is negative, it is decreasing. Okay, and this is in fact going to be continuous because we are never dividing by 0. Okay, so rational functions are only discontinuous when they divide by 0. Okay, so that means in order to determine whether or not the series converges or diverges, we look at the improper integral from 1 to infinity of 1 over x squared plus 1 dx. Okay, so first step is rewrite this as a limit. Limit as t goes to infinity of the integral from 1 to t of 1 over x squared plus 1 dx. So this is a basic antiderivative, if you don't remember. Antiderivative of 1 over x squared plus 1 is in fact arctangent. So this is going to be limit as t goes to infinity of arctangent of x evaluated at 1 and t. Okay, so plugging this in, we get the limit as t goes to infinity of arctan t minus arctan 1. Okay, so as t gets really, really big, arctangent of t goes to pi over 2. And arctangent of 1 is pi over 4. So pi over 2 minus pi over 4 is going to be pi over 4. Okay, so the fact that we got a number out means that the improper integral converges. So we'll say the improper integral converges. And then lastly, we can say that because the improper integral converges, it's a positive decreasing continuous function. The series converges by the integral test. Thank you.